I'll just announce. Okay, so welcome to another class of Math 410, and we are very pleased to have Professor Ajda.Fosner from U of Primorska of Slovenia. Long way to come here, and so she will tell us something about preservers on tensor products of Hermitian matrices. And all yours, Ajda.
Thank you. Thank you. Yes. First of all, I would like to thank Professor Lee to invite me to Williamsburg to give me the opportunity to have this seminar here, for all his help and hospitality, and for lunch today. It was great. Thank you. So, my name is Ajda.Fosner. I come from Slovenia, from the University of Primorska. Actually, I'm working at the Faculty of Management, where I teach statistics and financial mathematics. So this is somehow far from my research work that I will speak today. Yes, I have 2 pictures. Okay. I come from Slovenia, I said. Slovenia, where is Slovenia? Okay, Slovenia is here. This small country. This is Europe, okay. Here is Slovenia. We have just 2 million residents, so it is a small, really small country in the middle of Europe.
How many people are there in Virginia? Do you know?
Yeah.
Anyone know? 14 million?
Okay.
14 million?
So 7 times of Slovenians.
Okay. So Slovenia is really small. So next to Slovenia is Austria, Italy, probably no Croatia, Hungary, and so on. Okay, I have one picture more. You can see. And here is Slovenia. The capital, Ljubljana. I live in Maribor. And this is Koper, where my faculty is situated. Okay. Yes, but I don't drive every day to Koper because we have my faculty has 2 different locations. It is situated here, actually by the sea, but most of days I spend in Celje. It's a small city, really small city, where we have 1 department where I teach. So, but I was studying in Maribor, and my supervisor is from Ljubljana. Okay. Any questions about geography? No. Okay. So, I can start with my talk.
Control F.
Control
F.
I'm going to talk about preservers on tensor products of Hermitian matrices. These are classes about, Professor Lee told me about large data sets. So I will try to combine this with my work. Okay, page now. Outline of this seminar. First, I will speak about some motivation for our study, about linear preservers, the connection between our work, research work, and quantum computing. I will present some results, nothing deeply about proofs, but just some idea I would like to speak with you, and give some remarks. If there is any questions, or if my language is not, because in Slovenia I speak Slovenian language, I have to tell this. So if you have any questions, if you don't understand anything, please ask me. Okay? Okay. Start with matrices. You know, matrices are rectangular arrays of numbers arranged in rows and columns. We will speak about complex matrices, so the numbers inside of these arrays and columns are complex numbers. Applications of matrices are found in physics, probability statistics, social science and so on. In economics, because I work in the Faculty of Management, there we have, for instance, input-output matrices, or in the theory of games, there are matrices, and so on and so on. And also the major branch of numerical analysis is devoted to development of efficient algorithms for matrix computation. And also Professor Lee talked with you about the connection between matrices and large data sets. Okay? Yes. So, in this seminar, Mn will denote the set of atoms and complex matrices, and Hn the set of Hermitian matrices. These are actually self-adjoint matrices, so A is equal to A transpose conjugate. Okay? And another notations for determinant, trace, spectrum, spectral radius, rank of a matrix, which I will explain it later where we deal with it. So, yes, I said that we will talk about preservers. In the last few decades, a lot of results on linear preservers on matrix algebras, as well as on more general rings and operator algebras, have been obtained. Actually, one of the most active subjects in matrix theory is the linear preserving problem, which concerns the characterization of linear operators that leave certain functions, relations, subsets invariant. For instance, they preserve a determinant, trace, or something, for instance, spectral radius, spectrum, or something else. Already in 1897, Frobenius proved that a linear operator on n times n matrices satisfies the determinant of phi of A is equal to determinant of A. So this means that a map phi preserves the determinant of matrices if and only if our map phi is of this form or of this form. So A is mapped into, every A is mapped into UAV, where U and V are two matrices with determinant UV equal to 1. Or it is of this form, so that we have a transpose. Here, actually, these two forms, we say that they are standard forms, so standard form of a map. And this was actually already in 1897. The next result, actually 50 years later, more than 50 years later, Dieudonné proved that a bijective linear operator on matrices, on n times n matrices, maps the set of singular matrices into itself, if and only if there are invertible U and V, such that phi has this form or it has this form. So actually, phi must be of standard form. Yes. So, linear preservers, as I said, in the last few decades, a lot of results on linear preservers on matrix algebras have been obtained, and also besides linear preservers, also additive and multiplicative preservers have been studied a lot. So this means that we do not assume that our map is linear, so homogeneous and additive, but we just assume that it is additive, or we just assume that it is multiplicative. And another step further, it is actually surprising that we can get also nice results without any algebraic assumption like additivity or multiplicativity, linearity. And probably the first fundamental attempt to attack this problem was made already in 1949 by Roy. Later, this is newer results, Baribeau and Ransford studied nonlinear spectrum preserving maps, and there are now a lot of new also results in this direction. So we are going to be focused on preservers, on tensor products of matrices. What is tensor product? I know that you already know, just to refresh your minds. If A is an n times n matrix and B is n times n matrix, then the tensor product of A and B is this matrix. This matrix is actually Mn times Mn matrix. And we will denote these two notations like this. Yes. Now, as I said, one motivation for our study, for our results that I will present here, comes from linear preservers and general preservers. On the other hand, the motivation comes actually also from quantum computing. Already Professor Lee has talked about this in your classes. In quantum physics, actually quantum states of a system with m physical states are represented as density matrices. Density matrices, these are positive semi-definite matrices which trace 1. And if A and B are two density matrices, then the tensor product of matrix A and matrix B is a tensor state, of course, in a bipartite system. Yes. So, already Professor Lee talked about two problems. The first problem here is to find efficient methods to check whether a state is separable or entangled, on the other hand. So we actually ask ourselves, there is a question actually, if a density matrix, for instance, density matrix C is a linear combination of tensor products of density matrices A and B, AH and BH, where T1 to Tk there are positive numbers summing up to 1. This is one question. And another question here also is to characterize a map phi, a linear map phi, leaving invariant certain properties or subsets like leaving invariant spectrum, spectral radius, determinant, trace, or something else. In our talk, in this seminar, we will be focusing on this second problem. But we have to mention here also the classical Wigner's theorem in quantum mechanics, which states that a bijective map phi on the set of pure states that are rank 1 orthogonal projections, satisfied as a trace of a product A and B is equal to the trace of phi of A times phi of B, if and only if it is actually of the standard form. So A is mapped, every A is mapped into UA U star, U star, this is transpose, conjugate transpose. Okay. Or phi is of this form, where U is a unitary operator. This is actually a classical Wigner's theorem, and another result that I have to mention here also is a theorem result on preservers of entanglements, which says that a linear map phi maps the set of entangled states onto itself if and only if one of the following holds. So phi of A tensor B, so phi maps A tensor B into this tensor, or M is equal to N, and this second is true, where U1 and U2 are unitary matrices, and TK is identity map or transposition map. So tau K, I'm sorry, tau K. So this means that identity map that maps A into A, or transposition map that A is mapped into A transpose. Yes, this is a result on preservers of entanglements on bipartite, of course, systems. So on the tensor products of two matrices. Okay. Now our results that I would like to talk about. The first one speaks about preservers of spectrum. So what does it mean that a map phi preserves the spectrum? This means that the spectrum of an image of a matrix A is equal to the spectrum of A. So phi preserves one set, so the spectrum of yes, here we will be focusing just on Hermitian matrices. Okay, I didn't mention this. Just on Hermitian matrices. And a linear map phi preserves the spectral radius if the spectral radius of the image of a matrix A is equal to the spectral radius of A for every Hermitian matrix A. Okay, this is for Hermitian matrices on the whole space of Hermitian matrices. And it is known that a linear map phi on Hermitian matrices preserves the spectrum if and only if is of the standard form. So if it is of this form or it is of this form, where U is a unitary matrix. Okay, and another result, not yet on tensor states, but on the whole matrices, complex matrices. So a complex linear operator phi leaves invariant the eigenvalues of Hermitian matrices. So it preserves the eigenvalues of Hermitian matrices if and only if it is actually of this form. So every A is mapped into TAT, the inverse of T, where T is invertible matrix, or A is mapped into T, A transpose, the inverse of a matrix T, where T is invertible matrix, of course. Now, the result on preservers of spectrum of tensor states or on tensor products of matrices. Here is a little bit another situation. So we have a linear map phi on bipartite systems, so on Hermitian matrices, and we assume that the spectrum of the image of tensor states is equal to the spectrum of the standard of the tensor product of matrices A and B, Hermitian matrices A and B. So if a linear map has this property, then it should be of this form. So it is mapped, the tensor product, the tensor state is mapped into U tau 1 A tensor tau 2 B U star, where this map tau is the identity map, so A is mapped into A, or it is a transposition map, where A is mapped into A transpose. This is actually somehow standard form on bipartite systems. And similar result is for preservers of spectral radius. So a linear map phi on tensor products of Hermitian matrices satisfies that these properties. So the spectral radius of phi of A tensor B is equal to the spectral radius of A tensor B, if and only if phi is of this form. So we have U unitary U, tau 1, so it identity map or the transposition map, and lambda is -1 or 1. So this actually means what? That A tensor B, for instance, one example is mapped into A tensor, for instance, B transpose. This is one of the possibilities if this tau 2 is the transposition map. Here, I have to point out that we did not assume in this result that tensor states are mapped into tensor states. Of course, the result maps shows that tensor states are mapped into tensor state, but we didn't know, we didn't assume this. And the second thing I would like to mention here is that we assumed that a map phi preserves the spectral radius just of tensor products of matrices, not for any general matrix. So it may happen that phi does not preserve the spectral radius of a general matrix. So we also have some these kind of examples. For instance, if you just take A tensor B transpose, and we see that a map phi actually does not preserve the spectral radius of a general matrix C on Mn of Hermitian matrices, Mn times Mn Hermitian matrices. Okay. Now, preservers of rank 1. We say that a linear map phi preserves rank 1 Hermitian matrices if phi of A is of rank 1 whenever rank of a matrix A is equal to 1. Again, we are just talking about here about Hermitian matrices. And in 2008, Gao and Sang proved that an injective linear map phi on Hermitian matrices, so this is not the tensor products, preserves rank 1 Hermitian matrices if and only if is of this standard form or of this standard form, where T is an invertible matrix and lambda is 1 or minus 1. Okay, this is the result on the whole space of Hermitian, the whole set of Hermitian matrices. Now the result on tensor products on preservers of rank 1 on tensor products of matrices. It says that of map phi, a linear injective map phi, preserves rank 1 tensor products of rank 1 Hermitian matrices, if and only if there exists an invertible matrix T, such that phi is of this standard form. Again, tau k is the identity map or transposition map. Again, here we did not assume that tensor states are mapped into tensor states. And another thing is that we just assume that it is preserved the rank 1 that are preserved rank 1 matrices of this form, so A tensor B. Not for this may not be true for a general matrix C on Hermitian Mn times Hermitian matrices. Okay, these were results on some results on bipartite systems. We also studied, for instance, determinant preservers on Hermitian matrices, then some other norms on tensor states, on tensor products of matrices. And finally, actually, we managed to also generalize our results to multipartite systems. These results were that I was speaking about were on bipartite systems, but we can generalize them also on multipartite systems. And the first result on preservers of spectrum. So this means that we have more copies of Hermitian matrices, and we take tensor products of them. And linear map phi preserves the spectrum of tensor products of matrices, if and only if is of this form, somehow natural. It comes somehow natural from the bipartite systems. The proofs here are somehow, because of technicalities, are a little bit longer, but there is no. We just spread it from 2 by 2 from bipartite systems to 3, or the tensor product, or more than 3 matrices. And again, the result on preservers of spectral radius on multipartite systems. So we have linear map phi, which satisfies that the spectral radius of tensor products of matrices is equal to the spectral radius of the image of tensor products of matrices. Then phi is again of this, how can I say, classical standard form, where tau k are identity maps or transposition maps. So it is, one can be transposition map and another can be identity map. And another result on preservers of rank 1. So we have a map phi on tensor products of Hermitian matrices. Injectivity, yes, here injectivity is actually essential assumption. Then phi preserves tensor products of rank 1 Hermitian matrices, if and only if there exists an invertible T and lambda such that phi is of this standard form. So actually it comes from, again, from bipartite systems. We just spread it on a larger set. Yes, here I also have to mention that all these results were on Hermitian matrices. Actually, we cannot find yet somehow the results for the whole space of complex matrices. Even for eigenvalues, I think we cannot deal with this. The preservers on eigenvalues, since also for determinant, there are still a lot of open problems here. What I was also yes, so as I said, we were dealing also with determinant preservers. I said about spectral preservers of rank 1 preservers, rank preservers, also idempotent preservers, but there are still a lot of open questions, and the most interesting is to connect this and found the connection between these results and how we can apply it in quantum physics, quantum computing. Yes. I will stop here. Now I am free for any questions, any discussion, any connection with large data sets. So.
Okay, so since Professor Fosner keep referring to what I have told you, probably you've forgotten. So I sent her my talk I gave here. So that's why she said, "Oh, you have heard this, you have heard this, but you don't remember." No big deal, right? So any question related to this line of study? That's right.
I think you touched on this at the very end, but I just asked me to clarify. So the results were for injective maps, and the goal is to get bijective maps. Is that? Or
no. What do you mean here at the last?
Yeah, there were a couple that were for. You said something about trying to get the whole space.
Yeah, actually, no. The question is because we just deal with this map on Hermitian matrices, okay? But we would like to find analog results also for complex matrices, so that we take a map phi on complex matrices. So, but it is actually, you know, Hermitian matrices have beautiful form if you find it in a Jordan form. So you know that there are diagonal. So it is completely different when you take the whole space of complex matrices.
So precisely when you even talk about low dimension case, right? So if I have rank 1A, rank 1B tensor, 2 by 2, just 2 by 2 matrix rank 1, everyone know what is 2 by 2 rank 1, I hope. My linear algebra student. 2 by 2 rank 1B. So I send A tensor B, both are rank 1, send it to 4 by 4 matrix, right? Mn by Mn matrix. So I insist that a rank 1 tensor, a rank 1, a linear transformation will result in a rank 1 matrix. What can you say about T? Will T have some nice form? That will be the full matrix algebra problem. So can you?
In this form, we have a form. Is there one form listed down here that will not preserve the rank 1 tensors for general matrices?
Yes, if you take just A tensor B sends to A tensor B transpose.
Oh, okay, so that doesn't
that's
general rank.
Yeah, if you take, for instance, so 2 by 2, I can show you 2 cases. Yeah.
So you have an example that without injective assumption, then it is not of this form. So follow-up Greg's question is actually injective with bijective, of course, injective. So this result will be true for bijective map. The map eventually is bijective. So injective is better than assuming bijective. Because the assumption is weaker, therefore the result is stronger. Now, one would naturally ask, can I even do away with injective? And I think the answer is no. Right?
No, it's an example. There is example.
Is it easy to mention?
I don't. But there is an example.
I think you can send everything to a fixed rank 1 with the trace function, isn't it? The usual trace.
Yeah. Trace.
The degenerate map.
Yes. You take A tensor B, or every map is mapped into. You take one rank 1 matrix. Just fix one rank 1 matrix, and you take
trace of the A tensor B. Trace is summing the diagonal entry. So for those who have not seen this, right? So this will be linear map, everything. Obviously not injective. Everything is rank 1 very much. Or 0.
It's kind of a basic question. What is the spectrum and spectral radius of matrices?
The set of all eigenvalues.
Without multiplicity.
Yeah. So the spectral radius is the sum, the maximum of them. So if you take the norm, non-norm, absolute values.
So if A is identity, spectrum is 1. Eigenvalue is 1, 1, 1, 1, 1, depending on the dimension. If the matrix is diagonal matrix 1, 2, 3, 4, minus 5. So the eigenvalue 1, 2, 3, 4, and minus 5. The spectral radius is 5. There we go.
Yeah.
Maximum absolute value.
Maximum value of absolute values.
So again, talking about stronger, weaker assumption. Preserving eigenvalue will preserve all the eigenvalue. Preserving spectrum, I only preserve those distinct eigenvalue. So
Multiplicity.
formally, it is stronger because you assume weaker condition. Spectral radius is even weaker. You only preserve the guy far furthest away from the origin. You don't exactly know what it is preserving. Just preserve that quantity. That's quite surprising that you get all the results and they are very close to each other.
Yes, but this is just for Hermitian matrices.
For classical result, same thing. But
Okay,
for tensor, no, we don't know anything, I think.
Not yet.
Not yet.
Yeah,
So it's you guys who figure out what happened to general complex matrix. Even 2 by 2, 3 by 3, low tensor thing is very, I mean, you know the technique, you know how to do it. Don't worry about MM, this big. Big data come from small data. So you know how to do 6 by 6 matrix, then you can do 6 million by 6 million matrix, we hope. Not always work, but we hope. Yeah. Yes?
So I don't know too much about the application to quantum computing, but a lot of the theorems kind of rely on the existence of like these matrices T or U of V that you can put it in this, like you said, standard kind of classical form. So how useful is that? Is there generally are those matrices generally going to exist in a kind of quantum computing setting? Am I making sense?
Matrices does exist, but you mean the maps? If this kind of maps there exist?
Yeah, I guess
this is actually this kind of thing that you yeah.
I'm the one to answer, right?
Yeah.
Any physics major here? No, okay, then I can pretend I know physics. In quantum physics, of course, you know the closed system is quantum state. There are two forms, either vector state or the matrix state, the density matrix. You have seen this, some physics student, right? A unit vector will be vector state if you study quantum physics in the future. A density matrix will be what they call the mixed state, the general quantum state. If you have a closed system, what are the quantum operations you can create, you can apply of the nature in you? According to the phenomenon math model or the Copenhagen interpretation, there's only unitary operator. So the unitary matrix we study in textbook, yes, it exists. It's the kinds of matrix U times U star equal to identity. It's an extension of the orthogonal matrix we studied in 211. U times U transpose equal to identity in real case. In complex case, it's U times U star equal to identity. Is it real? Yes. The black box in the quantum mechanical world, if there is a closed system, if there is a quantum operation, it must be of this form. Okay? So those result potential application is that if you want to change for some reason, the Hermitian matrix, again, I pretend I know physics, right? Hermitian matrix corresponding to observable. Any observable you can do in the lab, doing measurement, you can transform the process into a Hermitian matrix, taking so-called inner product or the trace of that Hermitian matrix with the quantum state represented as density matrix. Okay, so you go to your app, you change your apparatus so that you change the Hermitian matrix to change the way you observe things. Is it possible to change it in such a state that it does not change the eigenvalue, it does not change the determinant? It may represent certain entropy or certain physical quantity you want to live invariant. You can do anything you like, but you want to maintain something that will not be changed. What are the flexibility? So you apply some transformation. And in quantum mechanics, linear transformation is the basic thing, because quantum mechanics, the premises is that all the things respect linearity. So one potential application is much theoretical, meaning in the lab, many operations easy for us to say unitary, in the lab, you go to physics colleague in this building, I talk to them. The NMR machine can handle 3 qubits, which amount to 8 by 8 unitary matrix. Not all of them. Mathematician can anytime write 8 by 8 unitary matrix, any type, use computer to generate one. In the lab, what they can produce is very special kinds of matrices like that. Go back to this kinds of result, the potential connection is that if I want to manipulate a system, the measurement, the observable, so that the bipartite state, A and B, they tensor together, and they leave certain thing invariant, the eigenvalue eventually are the same. The spectrum the same, I don't care about multiplicity. The maximum measure, which is the spectral radius, the maximum eigenvalue, absolute value is your machine. You don't want it to explode, right? You measure up to 100 minus 100, that is the maximum you can handle. Okay, so if the spectral radius is within that range, which means that my machine can do that. So all these results possible, have some implication that if you want to maintain that invariant, so in mathematics we say leave determinant invariant, leave the rank invariant. Why is it interesting, right? But there's some physical meaning for this determinant, rank, and eigenvalue. And you find the physical meaning, and I want to set up an operation. I have a super machine which can change the system, but I want to leave this invariant. How should I design the super machine? The answer is that, for example, UU star, which is a change of basis, which is very natural closed-state unitary operation, quantum operation in quantum mechanics. So the standard thing is the only thing you can do. So you cannot, I mean, you want to get a Nobel Prize by dreaming up some very clever transformation. Sorry, UU star is all you can do. Then you have to look at the local system, tau 1A, tau 2B, which means that in each local system, after this big change of the space, all you can do is that you flip to the transpose. Okay? In physics, there are two types of things. One type of thing transpose is not allowed. I don't remember those time, the relativity. So that is not even physical. So it's totally hopeless to do the transpose. But some new interpretation, some physics, you study more physics and tell me that some operation actually transpose makes sense. So you have to design a system, I don't know, reverse time or something, then transpose can exist. Okay, so good luck if you want to preserve the rank. I don't know when rank corresponding to what. All you can do in the lab is that to create a T which is invertible, okay, and then you create that. That is all the hope you have. That is one thing. You actually prepare your apparatus to do that. Okay, if it makes sense at all, right? Mathematically, I tell you that if you want to do this, this is the thing you want to construct. Another thing is even more interesting. I always think about this kinds of problem like this. Everyone is racing to do a quantum computer. So one day, a salesman come to this room saying that, oh, CK, I have a quantum computer. It really worked well. All right. I said, let me see. According to this theorem, if I put A1 tensor A2 there, under quantum operation, only certain kinds of B1, B2 can come out, right? Okay, so I cannot disassemble your machine to see whether it is a real quantum computer, but I can test. I fit some A1 tensor A2 there, B1, B2 come out, or U, B1, B2 come out, whatever. I examine that. I know how to compute matrix, right? So I look at the eigenvalue you input, look at the eigenvalue you output. I fit another C1, C2, you get B1, B2. Quickly, I discovered that it is not even of this form. But if your machine is a quantum computing machine, it should obey quantum mechanical rule. I should expect the transformation, the black box transformation, even without the formula. This kinds of thing in, that kinds of thing should be the output. You see, then I can say, no, you're cheating. I will not spend money to buy your machine. It is not quantum operation. Go home, right? So there are two things. You can construct your apparatus. You can test whether the apparatus makes sense because we prove mathematically, unless quantum mechanics says the math model is wrong. Otherwise, we prove that that is the only way you can obtain outcome from these kinds of input. So there are two major things I can see. These kinds of theoretical result may have interesting application or implication to quantum computing study. Except now like Professor Fosner, we do field mathematics and then we try to talk to applied people. And now I even ask them to do it like I said, I actually, Diane and I talked to the physics colleague, even how to test some operation we think is very trivial. On 3 qubit, so to speak, egg by egg thing. I was very surprised to hear that they can only do this and this. And even those 3 matrices, we know matrix multiplication is not commutative. We know always know that. What surprised me is that actually there are 3 types of simple matrices you multiply. It turns out that in the lab, you can do A1 multiply A2 multiply A3 easily. Does not necessarily imply that you can do A3 multiply A2. I don't want them to be the same, right? They cannot be the same. But even 3 same matrices multiplied in certain order, the machine, some will be more time consuming. I have yet to learn all those. So all this theoretical thing, how we use it is one story. How actually you go to the field to use it is another story. The best story in this class, I think that you guys interested in this big data thing, nothing is completely pure or completely applied until you can combine them. Pure idea, pure result, if you use it right, may have interesting application to applied subject. Applied question, if you ask interesting question, it becomes very interesting to use. Problem, right? Yeah, as long as you're interested and you're willing to learn, yeah, you'll get somewhere, some prize, some good result, I hope. Other question or story? Want to share? Tell? You check our Virginia population yet?
Oh yeah. Yeah, we're 8 million and Slovenia has 2 million people.
Okay, only 4 times. So.
Okay, I'm satisfied.
Okay. Any other questions? And you can always send email to Professor Fosner or myself. I can forward to her if you have further idea or questions or solution of any of those problems. 2 by 2, rank 1 to rank 1. Okay, work on it tonight. You get extra credit. I will talk to Professor Shi and to her.
Yes.
You get solve this over problem. You get an A immediately. Yeah. Anything else? Okay, if no, we thank the speaker again.